Hello there, everybody, once again, and welcome back. Today we are looking at a question from Unit E, and this is a question from IB Physics Paper 2, HL, May of 2025. The question is Rutherford modeled the scattering of alpha particle by gold nucleus. However, when initial particle energy greater than E naught, fraction of alpha particles scattered at angle close to 180 degrees do not follow Rutherford's model. Why deviation from model occurs? Now, when the energy of alpha particle is greater than a certain E naught value as mentioned in the problem, with all that kinetic energy E naught, the alpha particle ends up getting really close to the gold nucleus. Now, at such short distances, the strong nuclear forces take over, and that is where the deviation from the model occurs. Because the model in the first place never took nuclear forces into account. So when the alpha particle gets really close, strong nuclear forces take over and we observe the deviation. As simple as that. Let's move ahead to the next part. How E naught can be used to estimate the nuclear radius of gold. Interesting thing, if you recall from Unit E, the alpha particle is starting from a really far away distance, right, with all the kinetic energy. The whole purpose behind alpha particle and the gold nucleus being really far apart is to enforce the fact that the potential energy of the system initially, electrical potential energy, is zero, so that the only energy that the alpha particle has is purely kinetic. Alright, so the alpha particle starts off with E naught kinetic energy, and then it eventually approaches the gold nucleus, but it will not exactly hit the gold nucleus. It's going to stop at some certain distance. The point where it gets really close to the gold nucleus, that point is at a distance d from the gold nucleus. So at this point, the nature of energy of the system is going to be purely potential, because gold nucleus is at rest. The alpha particle also is at rest momentarily. So the energy of the system is purely electrical potential. So we can write the electric potential energy of the system right now. We can say this will be K times Q1 Q2 over D. This is the potential energy. Now, particle started off with E naught energy. All of that energy got used up in overcoming the force of repulsion, resulting in the alpha particle eventually stopping at d distance. So you can just conserve the energy at initial point and the distance of closed approach. So E naught equals to K Q1 Q2 over D. With the help of E naught and everything else known, which is electrostatic constant, the charge or the product of charge on the alpha particle and the gold nucleus, one can estimate D. And I believe the units of the magnitude of D, the order of D, falls very close to femtometers. All right, let's move to the next part. Gold 198 is a radioactive nuclide of gold, decays into stable mercury with an emission of beta particle followed by 1 or 2 gamma photons. All right, half-life of gold is 2.69 days. Calculate in seconds inverse the decay constant of gold 198. All right, now first things first, when you see that the half-life is given in 2.69 days and they're asking us to report the final answer in seconds inverse, the first thing that we need to do is convert this part 2.69 days into seconds. So for that, what do I need to do? 2.69 days with every day having 24 hours, with every hour having 60 minutes, and every minute having 60 seconds. Or I could have just multiplied it with what? 86400. Right? That's the number of seconds we have in a day. This will give me the half-life in seconds. Once I have this, I can go back to the data booklet. There's a formula about the half-life. It says T half equals to 0.69, or if not 0.69, you can just use natural log of 2 divided by decay constant. You can use this formula to calculate the half-life, the decay constant. So let's move to the calculator. All right, so I can say that the decay constant will be ln2 over this whole part, 2.69 into 86400. Just need to solve for the decay constant. So we have ln2 divided by 2.69 times 86400, and this is equal to 2.98, and I hope you can see the mu at the end. That's 10 to the power negative 6. So this is 2.98, or just 98 into 10 to the power negative 6 seconds inverse, right? And we are working with 3 significant figures, and 2.98 is fine. All right. A sample contains 5 milligrams of pure gold 198. Determine the mass of mercury 198 present in the sample after 1 week. All right. For this part, there are multiple ways to do it. You just have to pick any one of those. So either you can work with the formula n equals to n naught e to the power negative lambda t. That's one of the things you can work with. Or you can work with the half-life formula as well. You can calculate how many half-lives are there in 1 week, and then you can calculate the amount of sample that will remain, or the amount of mass of mercury 198 that will be formed after a week. So let's try this. All right, so we are starting off with 5 milligrams of pure gold 198, and then I can calculate how much of that gold will remain after a week. So I can do 5 times 1/2 raised to number of half-lives. I just have to figure out how many half-lives we have in a week. So a week has got 7 days, and we've got 2.69 days of half-life. So 7 over 2.69, that will give me the number of half-lives. I can just substitute this for n, and that will give me 5 times 1 over 2 raised to 7 over 2.69. So I can just go back to the calculator again. So we have 5 times 1 over 2, or you could just write 0.5. Either of them works fine. 7 divided by 2.69. So that's 0.823 milligrams. So this is the amount of pure gold which will remain in the sample after a week. But the question asks us to figure out the mass of mercury that will be present in the sample. Now, conservation of mass follows every time. All right, so the amount of gold that we had, only 0.823 milligrams of that remains as gold after a week, which means remaining mass got transformed into, or it got converted, or it decayed into mercury. So the amount of mercury formed will be 5 minus 0.823, which is 4.177 milligrams. Or since we are working with two significant figures, actually this is I can write it as 4.2 milligrams. That will be the answer to B2. Okay, so for the last part, gamma photons of the following frequencies are emitted during the decay of gold 198. Explain how this observation provides evidence that nuclear energy levels are discrete. Fine. So if you look at the frequencies, I've got 1 times 10 to the power 20, 1.63 times 10 to the power 20, and 2.63 times 10 to the power 20. If you think about it, discrete energy levels implies whenever the transition of nucleons, in this case, happens inside the nucleus, They transit from higher energy level to a lower energy level, and because those energy levels are fixed, we get to see only fixed frequencies. That's the first evidence that you can provide. The second and the most important evidence would be observing the frequency values, because if you think about it, there's a sort of cascading that exists here. I can see that the sum of frequency will result in the largest frequency. The sum of lower two frequencies gives me the highest frequency in the table, which implies if I have three energy levels and there will be three possible transitions, right? Now, let's say this is E1, the third to second level transition is E1, and this transition results in E2 energy, and this one is E3. E1 plus E2 equals to E3. If this sort of arrangement exists, that also indicates that there are discrete energy levels, and what we are observing are photons emitted during the nucleons transitioning between those energy levels. So these are the two observations that you can provide, which suggests that the nuclear energy levels are discrete. All right, so I believe we have discussed the entire question. If you've got any doubts, the comment section, as usual, is always open. I hope you guys understood this pretty well. If you've got any doubts, do let me know in the comments. Thank you for joining, and I'll see you in the next one. Goodbye.